sick and cancer develop and all kind of different stuff, right? So that's ionization. So it causes ions, and then ions are no good, right? Because ions are going to start reacting with everything that they can react with to become stable. Remember, when ions are positively charged, negatively charged, they want to stabilize. And then they go stabilizing whatever they want, and then that causes the function of whatever that thing is to start malfunctioning, and then you get a lot of mutation taking place throughout your body. The penetrating power, we have alpha particles, it's greater than beta, which is greater than the gamma rays themselves, right? So we have to know how these guys are really shaking out as you go along. How do we write these balanced chemical equation? We have these nuclear equation. They used to represent the changes that take place, right? When writing a balanced equation, we have to remember the mass and the charge, right? And we have to use the periodic table. We have to become fluent in that. So here, the total mass at each side of the equation has to be balanced. We did balancing regularly using coefficients. Now, we have to use those coefficients, but use the mass and charge. Mass and charge. Remember, the charge is on the top, the mass is on the top, the charge is on the bottom. Remember when we saw the beta particle had -1 and the position had the +1, gamma is 0, 0. Gamma has nothing, right? So here we have to look at both sides of the equation, pay attention to both sides of the equation, and these questions can come in that they can give you the particle that is emitted and ask you what is formed as a product. Or they can give you the product, give you the starting atom, and ask you what particle is emitted. But you have to go by the charge and mass.
Okay.
And both sides. Okay? Here, for instance, let's look at this one. Uranium. When uranium goes through a radioactive, uranium-238, right? Goes through a radioactive process, it forms thorium-234-90. 234-90. Now look at what's going on. You have to balance this out with an alpha particle.
Okay.
Right? Because 234 plus 4 gives me 238. 90 plus 2 gives me the 92. So that's how you have to play around with this. If they didn't give you
The 4?
if they didn't give you the
heat.
alpha particle on that end, and they just gave you the 238-92 and the thorium plus a big question sign, you have to come up with that because you're looking at the mass and you're looking at the charge and you're going to find which particle. If they didn't give it thorium, if they didn't give it thorium, you would have to go to the periodic table and find out who is 234 because you know it's 234 plus 4 gives you the 238, and then you see the 90 and it will fall right in line. Right?
Oh.
But it's a periodic table. Whatever they are missing is what you have to figure out what it is. Sometimes if they give you thorium and helium, the alpha particle, and they didn't give you this, then you got to go find
out
238-92.
Got it.
Because again, it's kind of tricky, right? Because remember, uranium has isotopes. So sometimes it might not be 238, or you're right? It might be 235, it might be something else, but you have to find. And that one might be emitting more than one particle. Right? So it depends. They can play around with this. They can get funky and crazy.
So you're saying it could be either uranium or the thorium, whatever, the TEH?
They can omit this and give it these two. Or they can omit this, give it these two. You got to come up with that. Or they can omit this, give it these two. You got to come up with that.
Come on.
Uranium is harder to find.
Right, that's what I'm saying, yeah.
No, but no, not necessarily. But they forms of uranium.
I know, okay.
But you have to look at those numbers, the math.
So would we typically see the 238 for uranium?
Thank you.
That's the one that's from the periodic table. But you have other forms of uranium.
Okay, good, thank you.
It always going to be 92 anyway.
Okay, all right, okay, good.
Because remember, we're talking about nuclides, right? Remember, we're talking about that they have different nutrients. Right?
Yeah, okay.
Okay, So look at this, a beta decay. Upon decomposition, nitrogen 16 produces oxygen 16 and a beta particle, right? So notice what's happening here. The atoms of these elements are changing to give you something new. Look at the new stuff that's forming, right? So here you have nitrogen 16. It has seven protons. They tell you it goes to a beta. So it's 0, -1. So whatever you choose here has to be 16. Because 16 plus 0 is 16. Brings me back here. Here is 8. But whatever the charge is on this particle has to be something that when you subtract it, you get 7. So 8 minus 1 gives me 7. So that's how they know it goes to a beta decay or it forms the oxygen 16. Okay? It's just playing with the balancing. It's balancing. Positron emission, right? Unlike the beta decay, the product nuclide has the same mass as the parent, but the atomic number has decreased by 1. Right? Notice what's happening here again.
Sorry.
We have carbon, right? 11. Right? We have boron 11. We just saw that up front. What changes here is the charge. Right? And why do I say this is charge? Because that's a charge.
Okay, you can see the positive. Yeah, good. Yeah.
So even though, here now we're talking about charge, but we're not seeing a plus or a negative, but we got to understand that these are the charges. Those are the protons in the nucleus, right? Here, 5 plus 1 gives me that 6. 11 plus 0 gives me that 11.
Wow.
So it's just math. It's just doing the math, looking at it, right? How else can we represent it? By the different symbols, the other symbol, right? That's the same positron, right? There are 2 ways we represent positron. The plus, because remember it's a high-speed electron, right? That's what the positron is. So either we use the symbol of the electron or we use the beta.
Okay. Symbol.
With a plus. The beta symbol with a positive charge.
For the positive emissions.
Positive. All right, the gamma production. Let's look at gamma now. Gamma, we said, had the highest energy, right? It's pure energy, we said. Most point penetrating power, right? It occurs to increase the stability of an isotope, right? The isotope is unstable, right? It needs to stabilize. It emits the gamma, right? Here, the atomic mass and number do not change. Why the atomic mass and number do not change? Because it's 0 mass, 0 charge, right? 0, 0. So here, what we see, right? We have the tenectic tom. That's always difficult for me to pronounce. But here you see nothing really changes. It's 99, 99, 43, 43. But it just emits a gamma. Nothing is changing, right? It emits a gamma. Usually gamma is emitted along with an alpha or beta particle. So when you look at some of these reactions, is either going to have a plus a beta or plus an alpha, right? Normally they emit with one of those two.
Alpha
right?
or beta.
Right? But this is a simplified way of looking at it. Here, this is what I was talking about, predicting the nuclear, when the nuclear decay. So here, in this case, they told you what is X. That's what I'm trying to get you to find out. What is X? Notice uranium is 239 now, right? I said they're different isotopes, right? So it's 239.92. They're saying, what is this guy? -1 would give me 91, 239. I got to go to the periodic table, find out who is 91, right? It must have 239 up top here because the 239 and 0 got to add up to that, right? So it's a periodic table. You have to have that, identify that, and that becomes Neptunium. Yes.
Is it 91 or 92?
It's 91, right? 93, sorry. 93 minus 1 give me the 92.
Oh, okay. I didn't want to
So
say
you
no.
get Neptunium at that point.
Yeah.
So notice now, this is one of the new atoms that are formed, right?
Uranium.
As uranium decays via a beta decay process, right? So again, here's one you have to look. Make sure 239, bam, bam. What's going to give you 92? It's 93. Then you go to the periodic table, you look up. Don't try to look for 239, okay? That's not what you're looking for. You're looking for the
93.
atomic number that identifies the species.
Because the beta particle is actually the fast-moving one, which will increase decaying of the uranium quicker, right?
Well, it's emitting it.
It's emitting the uranium. Okay.
Because look, reactant product.
Okay.
So it's giving that.
All right. React. Okay.
Right?
Yeah.
Just look at it from that.
Yeah.
perspective,
Okay.
Right? Binding energy. Okay. What we need to know about binding energy, right? Remember we talk about stable and unstable. Some of them just naturally decay. Well, they have a ring, right? They have like a nice little corridor. I'm sure it's in your book, right? That tells you where unstable isotopes lie and where stable isotopes lie on your periodic table, right?
Oh.
It's a very, it's not a tricky thing, but it's a very short window, right? That you look into these elements having a certain mass, right? That tells you that these guys are going to be radioactive. Let me see if they have it in this particular book. They should have it. No, I don't see they have that particular graph. Anyway, no, they don't. I don't see they have it. Why? Why do they have it? This is something should be. Okay. All right. So we deal with it from here. So binding energy, we're talking about the energy that holds the protein, neutrons, and other particles together in the nucleus, right? That's the binding energy holding these things in. When a nuclide decays, some of the energy is released because the products are more unstable, right? Here's the ratio that I was talking about, right? There's this graph that gives a really nice, right? The ratio of the protons, right, inside of the nucleus. So when you have a nucleus with large numbers of protons, 84 or more, they tend to be unstable. Those that are lighter tend not to be. Isotope with a magic number, right? These are the ones, 2, 8, 20, 50, 82, and 126. Protons and neutrons are stable, right? When you have these number of protons and neutrons, you have a stable atom or element or nuclide on your hands, right? Well, where are these guys? You can also think about the energy levels, right, that are within the nucleus that are causing this stability to take place. So note again, when we look at those guys, 84, right, protons or more, they're going to be unstable. That's why when you look into the lanthonide and the actinide series, you know those two pieces, those two rows that are pulled out and put in the bottom of your periodic table, right, those are they're normally, all of them are radioactive, right, they're radioactive. Those are the radioactive row, right, that you're going to get. And they're lying somewhere where the 84 or more protons, right, that they contain. Half-life, right?
Yeah.
Oh, we're coming close to that time. half-life, here half, and it goes for your medicine, right? Tell me about it.
Okay, so you with the radio. Okay, so what it is like if you buy a bottle of aspirin, right? It has a half-life on the shelf. So the longer it remains there is how it loses its the product.
Potency.
Yeah, the potency, correct? So the half-life, like you have dating and the carbon and so forth. So with the half-life, it just shows you that when you have a product that's just there for a long while, it goes through this half-life thing.
Yeah, I more like to think about it when I'm interacting with it.
Yeah, right.
It's sitting on the shelf. But that's a good example.
Okay, thank you. Go ahead.
When you take the medication and it's the time period for when it starts to work, and then it has like a resting period and then it starts working.
Not really a resting period, right? What happens with the half-life, and this, he didn't bring up my pen.
I ain't got nothing to give you. I'll give
Right?
you.
The half-life works when you take medication, potency, right? It has a certain amount of time when half of it disappears,
Okay. All right.
right?
All right.
You have the pen. You have the pen.
Go ahead, girl.
Yeah,
Get your
mark.
credits, girl. Go
Who
ahead.
has the marker?
You gave it to the man.
I know I gave my marker. You have one.
Which man?
No, I don't.
Who has the marker that was?
Oh, no.
God, I wish I had one. I'll get extra credit. Damn. Nobody ain't got a marker? Come on. Go ahead.
I thought you was bringing back the marker. Thank you, sir.
10 points.
Okay, no, that's okay. No. Don't
All right.
put it
Okay.
Why not get excited? Because it's a plus 10 and minus 10. I'm going to write some on the paper and throw it at you, whichever one you catch.
Oh, God, that's good. You got.
Okay, so here's how the half-life works, right? And I think we will stop. You have only a few questions, not a lot of questions. Okay, so here's the deal, right? This is an exponential decay. So let's say we started at 100 here with our medication, right? Somewhere between here, we get to 50, right? And eventually we get to 0, but we never get to 0 because if you know anything about exponential decay, it never hits the 0, never. It just keeps going on and hugging that line, right? Because whatever half you have to take a half of that half. So for instance, this is the first half-life. T half.
It reminds me of like
Right.
Baltimore.
If you do your second half-life, how much of the 100% would you have remaining?
50.
That's right. What?
50. Oh, sorry. 25. Calm down. Okay.
Right. So when I have 25 left, let's say 25 grams or 25 milligrams, right? Over some time, it might be days, it could be seconds, it could be minutes, it could be hours, it could be millions of years or years, right? We use iodine, right? When we have a thyroid problem, it's a chaser. Eventually just works its way out, right? That's have a half-life, particular half-life. So now, what would be my third half-life? Because this is my first half-life, right? This is my second half-life, right? My third half-life, how much do I have? 12.5.
12 point, yeah.
Right?
Oh, okay.
That's my third half-life.
12.5.
Right? Then at 12.5, I have to go to half of that, right? So half of the 12.5 is 6.25.
Oh, okay.
6.25. Then I have to take a half of that. So you see, anything you have remaining, if there's anything remaining, you gotta get a half. This is how the half-life works. Okay? So this is going to be your first half-life, second half-life, your third half-life, and so forth, right? Then you go down to your fourth half-life and all that.
So what about canned goods? Canned food?
That's shelf life.
Yeah, that's the same different,
It
right?
can work basically the same, but I don't think when you put a canned food, you can determine directly what that half of whatever is going to remain. This goes for chemicals, medicine,
Okay.
and things of that nature,
All right,
right?
yeah.
So each radioactive isotope has its own half-life, right? So you have things that can be around for billions and billions of years.
Okay.
Right? Now, why is it that they store radioactive waste from the fuel rod